Okay, so continuing on with slope. The rate of change is the same as slope. Slope is a rate of change. A change in one quantity relative to the change in another. So what happens to one when something else changes? So we always have to have units, something like kilometers per hour, meters per second, things like that, dollars per month. The slope of a graph describes that rate of change. It's showing the relationship graphically. It's giving you a visual representation. So just describe the rate or determine the rate of change, of 12 donuts that cost $7.20. So what we're going to look at is 12. Sorry, I'm going to just make that a little smaller to look at. So we're going to look at 12 donuts over $7.20. Now the rate of change here, all we have to do is 12 divided by 720, and we're going to get 1.67 donuts per dollar. Okay, now I could switch that around and I could say 720 divided by 12, and I could say that it's 60 cents per donut. Okay, it depends on how you're looking at it. Okay, both of them would be correct because we haven't established which one's dependent and independent. We haven't said like you have X amount of dollars, what are you finding, or how many donuts can you get with this. Determine the rate of change if an adult breathes 37 liters every 5 minutes. Now we know time is going to go on the bottom, so here we're going to have 37 liters over 5 minutes. So what this is going to tell us is we can do 37 divided by 5. We're going to get 7.4 liters of air per minute. Okay, we just need to represent it with units. Excuse me. If the following graph is showing fuel consumption, so we're looking at the volume of gasoline left in a car's tank. Now, it actually makes sense because we start with a full tank and then we're going down towards empty. So it says calculate the slope of this graph. Well, the slope is going to be 70. It's going down 10, 20, 30, 40, 50, 60. So the slope is going to be negative 60 over 50, 100, 150, 200, 250, 300, 350, 400, 450, 500. Okay, now I counted that all up just to make sure that I was right, but you could quite easily see that it was 500. So what this is going to give me is we're going to do 60 divided by 500. We're going to say that this uses 0.12 liters per kilometer. Okay, we're dealing with liters and kilometers there. Interpret the slope as a rate of change. So the graph, so this is showing the liters per kilometer. And this car, like we just said, is 0.12 liters per kilometer. Now it says determine an equation that represents this. Well, we know rate of change. We talked about this in the last note. We know we can set up an equation that's y equals mx plus b, where m is your slope, so we have 0.12, and b is our y-intercept, which is where we hit the y-axis, which is 70. So there's our equation that represents this line. Okay, so slope from first differences. So if we look at this, if we graph these two graphs, we've got 0, 0. So I'm going to just assume that for argument's sake, let's go our x's every other box is 1. What are we counting up to? 4. So we'll just stop there. And here, we'll say every other box again is 1. I might not get everything in, so 1, 2, 3, 4, 5, 6, 1, 2, 7, 8, 9, 10. That's okay. So we start at 0 and 1. So 0 on the x, 1 on the y. Then we go to 1 and 2. Then we go to 2 and 4. Then we go to 3 and 8. Now what we should notice here is we're not actually going up by a constant amount. This isn't a straight line. This is a curved line. Okay, so these dots are forming a curved line, not a straight line. This is non-linear. Well, what we can do is, as long as our x's are all changing by the same value, now I'm going to show you what I'm doing here. What I'm doing is I'm looking at the difference between 3 and 4, the difference between 2 and 3, 1 and 2, 0 and 1. And all I have to do is subtract from the bottom. So subtract up the table. So I'm going to do 4 minus 3 is 1. 3 minus 2, 1, 1, 1, 1, 1. Okay, now I'm going to do the same thing on this side. Okay, these are called finite differences. So I'm going to subtract, we get 8, 4, 2, 1. Well, these are all different. What that actually tells me, if the first differences are not the same, this is non-linear. The first differences need to be the same for this to be non-linear. Or sorry, for this to be linear. So if we look at the next one, we'll do the exact same thing. 1, 2, 3, 4, 5. We'll stop there, and this one will go, oh boy. 1, 2, 3, 4, 5, 6, 7, and we'll stop at 8. So we start at 0 and 7. Then we go to 1 and 5. We go to 2 and 3. We go to 3 and 1. And then 4 is actually a negative 1. I'm going to stop there because I'm going to just draw this line in. And we can see that we've got a straight line. But how could we do this with the table? Well, we know that these are all 1. And what I'm actually finding on the left is I'm finding the change in x. We know slope is the change in y over the change in x, delta y over delta x, y2 minus y1 over x2 minus x1. So we can now do the same thing. Now remember, we're subtracting up the table here. Negative 1 minus 1, that's negative 2. 1 minus 3. That's negative 2. 3 minus 5. That's negative 2 and negative 2. So all of these being the same shows me that this is a linear graph. The next thing I can do is I can actually find my slope. I can take the change in y and divide it by the change in x. Negative 2 over 1. So I know my slope is equal to negative 2. Now it says write an equation if they're linear. Well, all we have to do then is find out where our y-intercept is. That's where y and x is 0. So y is equal to 7, where x is equal to 0. Or we could look at our graph and see that. So our equation is y equals mx plus b, where m is our slope, negative 2, and b, in this case, was 7. It's always where the graph crosses the y-axis, where x is equal to 0. Okay. So looking at this question, this example shows a table, shows the height compared to the ground of a snail crawling up a pipe. So it says add the first differences or column to determine if it's linear or nonlinear. So what we have to look at here is these ones are all changing, but they're all changing by the same amount. It's 3, 3, 3, 3. Okay. Now these ones are also all changing by the same amount. 13 minus 9 is 4. 9 minus 5 is 4. 4 and 4. So we're good. It says calculate the slope. Well, we know the slope is equal to the change in y over the change in x. Now we need to choose two that are the same group. So I'm choosing these points. Okay, so we've got 4 over 3. Okay, so there's our slope. Interpret the slope as a rate of change. Well, what this is telling me, if I look at the units, I'm going to change colors here. If I look at the units, our y value is meters and our time is in minutes. So this is saying the snail climbs 4 meters every 3 minutes. Is this partial variation or direct? Well, this is partial because we start at -3. Now write an equation. If we start at -3, that's our starting point. That's our y-intercept. Knowing, again, we have y equals mx plus b. Y equals, we know our slope is 4 over 3. And our b value in this case is, it's going to be plus -3. Well, that's actually y equals 4 over 3x minus 3. Because a positive and a negative is a negative. All right. To summarize, to be allowed to use first differences, what must the values of x be like? They must change by the same amount. They must go up sequentially. How do you tell from first differences if it's linear? If the first differences are the same? And when we're talking about first differences, we're only considering the y's. We can't actually find first differences if the x's aren't going up by the same value. If the x's are going up by a different value, we can't look at the y values. How do you tell from an equation if a relationship is linear or nonlinear? Well, a linear equation won't have any exponents. So no exponents. Is linear. There's some other things that will make it nonlinear, but for what we're looking at, a linear equation is going to look something like this, or something like this. It will not look like this or this. It won't look like anything like that. So those have exponents, so it can't be that. Here are some questions for this.